Hello class, welcome back. We're going to continue today with Carbohydrates Part 2. Carbohydrates Part 2. Let us do a little review of what we talked about last time, however, just to see if we understand everything here. Our simplest, I like to call it our simplest carbohydrate, is going to be glyceraldehyde. And so if we have here C, glyceraldehyde is an aldehyde, and so that's the aldehyde functional group. And then we have C, and if we put OH here, I'm going to draw it in a Fisher projection, H here. That's how it only has one chiral center, and then we're going to have CH2, OH. And this number 3 carbon is not a chiral center. And so this molecule is glyceraldehyde. This is carbon 1, carbon 2, and carbon 3. Now, as it's drawn, this compound is diglyceraldehyde. Diglyceraldehyde. And that's because this carbon here is a chiral center, and it has the R configuration. And so this molecule is diglyceraldehyde because it has a D configuration. This is diglyceraldehyde. Oh, because this carbon has an R configuration. Does that look like an R or a 12? Okay, glyceraldehyde. And so diglyceraldehyde, because it only has one chiral center, is the same as R-glyceraldehyde, because there's only one carbon. Okay. Now, all of your D carbohydrates, the highest number chiral center is always has the R configuration. But before we go to one of those, I want to draw, just as a comparison, I want to draw L-glyceraldehyde. All of the carbohydrates that are found in humans, all of those are based on D-glyceraldehyde. All of the amino acids that are found in humans are based on L-glyceraldehyde. So, D-glyceraldehyde and R-glyceraldehyde, they are mirror images of one another. And so if I were to draw R-glyceraldehyde, I would put here C. It doesn't matter, since this is not a chiral center, it doesn't matter how the number 1 carbon is drawn. I'm going to save this. I'm going to save the chiral center, and I'm going to draw the number 3 carbon, CH2OH. And so it doesn't matter how those are drawn. Now, to make the mirror image, what we'll do is, instead of putting, as a Fisher projection, instead of putting the OH on the right side, which makes it R-glyceraldehyde, we'll put the OH on the left side. And that makes this, and so that's going to make this L-glyceraldehyde. So D and L refer to the whole molecule. R and S refer to the carbons, the specific carbons. But since glyceraldehyde only has one chiral center, you only need to, if you identify if it's R or S, you know what the entire molecule is. Glyceraldehyde. Does that concept make sense? It'll really, if it doesn't, I'm going to really drive it home when we go to a 4-carbon compound, and you'll really be able to see. And so this is L-glyceraldehyde. And so this chiral center here on the number 2 carbon, what is the configuration of this chiral center here? S. It's going to be S. Make sense? Excellent, excellent. Now, let's go to a 4-carbon compound. Let's go to a 4-carbon compound. And now, whenever you add another carbon, and if you want to still keep D, since this is the number 2 carbon, this has to become if you want to keep this D, you keep this configuration here, and you just add another carbon at carbon 2, and you move the 2 down to 3. So let's make another, let's make a 4-carbon aldehyde. What is a 4-carbon aldehyde called? Aldotetros. Very good, very good. So let's put our aldehyde functional group here, COH. That's our aldehyde. And so we're going to put our carbon here. Carbon 2 is a chiral center. I'm not going to put what it is yet. Carbon 3 is a chiral center. I'm not going to put what it is yet. And we're going to put CH2OH. Now, we want this aldotetros, we want this carbohydrate to be D, And so there's one, in order for a carbohydrate to have a D, the whole molecule to be a D molecule, there's one requirement that must be met. What is that requirement? The R, there has to be an R where? No, on what? But there are 2 chiral centers. The highest chiral center, exactly. And so here, in order for this to be D, we have to have, in a Fisher projection, just put the OH on the right. And so this becomes an R chiral center. And so this is D something. That makes it D. That's all you need to remember. So on all of the molecules that are found, all of the carbohydrates that are found in a human body, that highest chiral center is always on the right. It's always R.
I thought the CHO had a higher priority than the CH2OH.
Yes, it does. But see, when we say the highest chiral center, see, this is carbon number 1 because it has the highest priority. This is carbon 2. This is carbon 3. And so there are two chiral centers. Carbon 2 has a chiral center and carbon 3 has a chiral center. But in order for this to be D, carbon 3 has to have the R configuration. That's what we mean. The highest numbered chiral center has to be R. That's what you get. That's the take home here. That's what you need to understand. Exactly. Again, this is 1. This is carbon number 1 because of this aldehyde functional group in priority now. This is carbon number 2. This is carbon number 3. The highest numbered chiral center has to be in the R configuration for it to be D. Does that make sense?
Does J matter what it is?
It does. I mean, but not in terms of D, in terms of D or L, but it matters what it is in terms of what that molecule is. And I'm going to have to show you some examples. Okay. Her question was, do the other chiral centers even matter? And I said it does matter. Well, it doesn't matter in terms of D or L, but it does matter in terms of what the name of that molecule is. And that's what we're going to go over now, because I need to drive that point home. Question.
You said the highest number chiral center must have the R configuration?
Has to have, for it to be D. The highest numbered chiral center has to have an R configuration for that carbohydrate to be a D carbohydrate. There is nothing is more important than that when talking about biochemistry and carbohydrates. Nothing is more important than that point. You have to know that. Yes, question.
So if it had, say, 10 carbons, same rule applies.
Exactly. Exactly. What would be the highest number if it had 10? Okay, her question was, if it had 10 carbons, does the same rule apply? The highest number chiral center still has to be R for it to be D. And that is correct. And now my question to you is, if a carbohydrate had 10 carbons in it, what would be the highest numbered chiral center? 9. Exactly. Make sense? Okay. Now, this compound is D something. Okay. And now, based on, so let's do, so The OH for 2 can either be on the right or the left. So what I'm going to do, I'm going to copy. No, I'm not going to copy it. I'm going to draw it over because that wouldn't be fair for you. Question? Do you have a question? Okay. I'm going to draw this over. C. I'm going to still make this D. OH. H. CH2OH. And now this is D something. They're both D. They're going to be isomers of one another. But now we give them different, their names, what the molecule is based on which isomer it is. So I'm going to erase this now. So we can name these compounds. Okay. Now, if that, let's do 4. If carbon number 2 has its OH on the right, if its OH is on the right, we call this compound erythrose. It's a completely different carbohydrate now. That's erythrose. If carbon number 2 has the OH on the left, we call this OH on the left. Does anybody remember what it's called? Threose. But they're both D. They're both D. Why are they both D? Exactly, because that highest numbered chiral center, that third carbon, is on the right. The OH is on the right, so it's D. All of the carbohydrates in your body do they have R configurations or S configurations? The carbohydrates in your body, do they have R configurations or S configurations? Depends on what carbon, if it's R or S, because the two could, something like glucose, some of the carbons are R, some of them are S. But if I ask you the question, the carbohydrates in your body, are they D or L? D. They're all D because that highest numbered chiral center is always R configuration. But like glucose, like on some carbohydrates, maybe the third carbon, if it's not the highest, maybe it has an S configuration, or maybe the second one or maybe the second one has an R configuration, or maybe the fifth one has an R or an S. It can matter, but that doesn't matter. Only the R one do you always know. It's always S. It's always R. The highest numbered chiral center. Does that make sense? Have to get that. Question.
Why is, okay, I see how you get them arranged, but why is it when they're arranged differently, they become like the two different molecules?
Because this is okay.
You got the OH on one side,
Mm-hmm.
the H on that, and this erythrose, but then on the threose you got swaps, and you got threose. So why is it like that?
Okay. Her question is, like on erythrose, you have the OH on the right side, and threose, the OH is on the left side. They look like the same molecule. You could just switch the OH and the CH and the H around, and it should be the same molecule. Why is that? And I didn't bring a carbon. I didn't bring any models with me. But what we're going to do, we're going to have to do this in lab because you all really need to understand this. When we do, not this week's lab because we have something for this week's lab, but in the next lab, we're actually going to make some carbohydrates using some molecular models, and you'll be able to see that. I could just do it. Oh, let me do it. Would you make sure that can get me on the board here? Remember when I drew this? This is what I want to see. This is what you ought to see. Oh. See, if you look at this on your iPad, you won't be able to see what I'm talking about. But remember here, if you have a chiral center, there's only, how can I explain this? There's really no way to explain. It's hard to explain. It's really hard to explain without actually seeing those 3D models. It looks, yeah, let's just go back here. Go back here. I really need those models to be able to explain it to you, because if I were you and if I were looking at these two, I say, well, I could just switch that around. I could just turn that and it's going to be the same molecule. But it's not going to be, because this is not planar. All of these molecules aren't planar. They make tetrahedrons. They make tetrahedral structures. And those angles, those 109-degree angles, once you turn it around, things are going back. And you have to remember for your Fisher projections, all of these are projecting outward. All of these are projecting outward, and you really need to. You just have to wait till it's going to be. It's hard to explain here.
So are they not aldotetras anymore, or are they both still considered aldotetras?
They're both still aldotetroses, because you have aldo here and you have 4 carbons. So both of these are still aldotetroses. Okay. Now what I'm going to do, I'm going to do something. Now I need you to see the difference. What's the difference between D-erythrose and L-erythrose? You know the difference between D-erythrose and D-threose. 1 carbon is different. So let's do this. Question first?
You know you had the D-erythrose and the D-threose.
Mm-hmm.
They're still considered aldotestrose. Okay. Is the D-erythrose or whatever? Are those like the common names of the carbohydrates, or like?
Yes, those are both of the common names. There is the common name and the scientific name for both of these. Like D-erythrose and D-threose, those are the common names and they're the scientific names for these compounds. Her question was, are these names common or scientific? And they're both. Okay. Now what I'm gonna do here, I'm gonna draw. It doesn't matter which one I draw. So let's do D-erythrose. So I'm going to draw D-erythrose here. Okay. This is D. What is this compound? D-erythrose. Okay, how should I do this? Okay, I'm going to do it this way. I'm going to draw a compound. I want you all to tell me what it is. Okay, here, I'm going to do this. Not going to do that one yet. Not going to do that one yet. Okay, now what I'm going to do, put OH here and H here. Okay, this compound that I'm about to draw, is this D or L? Okay, it's L. That is correct. How do you know it's L? Exactly. The third carbon, or the highest numbered chiral center, is on the left. Okay. Now, okay, so it's L. Now I'm going to draw something here. Okay. So now, what is the name of this compound here? L-erythrose. Does that make sense? That's not right. And now I'm going to explain to you all why it looks like it should be. But whenever you have the D and the L isomers, they are complete mirror images of one another. And so in order for this to be a mirror image, the OH has to be here. Everything has to change. all of the chiral centers have to switch places. Exactly. That was L3os I had before. Exactly. And so this is L-erythros here. And the one thing you need to remember about L and D's, they are called enantiomers because they are mirror images of one another. They mirror one another. And all you have to, when you talk about the mirror image, it doesn't matter what everything else is. Just look at the chiral centers. Can you see that this here and this is all that matters? Can you see that they're mirror images of one another? Because here, like there's an H, H, O, O. As you go out, they just mirror one another. They're mirror images. And the one thing you're going to be thinking in your mind now is they're the same molecule. All I have to do is flip that over, and it's the same thing. But remember, we're doing Fisher projections. So in a Fisher projection, they're not. And you really have to work with 3D molecules to see that. So they're mirror images of one another. And so if molecules are mirror images of one another, they are called enantiomers. One of the stupidest words in chemistry, but here we are. Enantiomers. They're mirror images of one another. Can everyone see that okay? Read? Sing? Make sense? Kind of? See, I don't really have time in lecture to put all the models together, but we will in lab. We definitely will do that in lab. And so here we have D-erythros and L-erythros. The chiral centers mirror one another. Everyone okay with that? Okay. And let's do the most famous. And again, these are both aldotetroses. Now, let's go back. I need to give you one more word. One more word here. Now, D-erythros and D-threos, are they mirror images of one another? They're not mirror images of one another. Are they isomers? Yeah, they are isomers because they have the same molecules, but they are not mirror images of one another. We would not call these enantiomers. So we would not call these here enantiomers. So these are not enantiomers. So I'm going to put it here just so you know enantiomers. I'm going to put a big X because they are not enantiomers of one another. When you have isomers that are not enantiomers of one another, but they have the same basic structure, we call them diastereoisomers or diastereomers. D-I-A-S-T-E-R. Make sure I get this word right because this is a diastereomers. So they're not mirror images, but they're still isomers. And so we call them diastereomers. Exactly. But diastereomers are more than just... See, they have the same number of chiral centers. But their chiral centers, they're opposite of one another. They have one or more opposite chiral centers, but they're not mirror images. Question. Yeah, they're not mirror images, but they're isomers. Her question was, What is an isomer? Yeah, what is an isomer? An isomer is a molecule that has the same number of atoms, different atoms. Like all carbohydrates are C1H2O1 because it's just hydrated carbons. And so this compound is C4H8O4. Both of these. And so they're isomers. They have the same number of chiral centers, and some of them are opposite of one another, but they're not mirror images. And so they are called diastereomers. But if all of the chiral centers were opposite of one another, that means they would be mirror images, and so then they would be enantiomers. But these are not enantiomers. D and L's are enantiomers. Everything else is not. Make sense? It's a lot of information here, because I could give you some really great test questions on this, just to make sure. Yes, exactly. Yes, C, yes. The parents are, but once you start oxidizing them, you can oxidizing them, and then they don't have that configuration anymore. Some people still consider them carbohydrates, but then when you oxidize, feel like if you oxidize the aldehyde, then it becomes a carboxylic acid, like glucose would become like gluconic acid, and then if you oxidize the other end, then glucose becomes glucuronic acid. And so it just depends on the level of oxidation. Okay. Should I do one more? Okay. So I think you understand this. We could go a long ways with this. I really need, now this is 4. I'm going to skip 5 because I really need to go to the carbohydrate that is really important, because I didn't go over it before. Any more questions about this? Let us talk about, what's the most famous carbohydrate in the world? Glucose, exactly. So let us draw glucose. So how many carbons is glucose going to have? Do you think is glucose an aldose or a ketose? Most of the time. Well, yes, glucose is an aldose. So 1, 2, 3, 4, 5, 6, CH2, OH. Now, the glucose in our body, is it D-glucose or L-glucose? It's D-glucose, exactly. So if it's D-glucose, what one thing must we know about glucose then? The 5th is R. And so if the 5th is R, that means on which side is the OH? It's on the right. So we're trying to make D-glucose. And so the others, you just have to remember. So whenever you have a carbohydrate that comes out of the body, it has to be D. That highest numbered chiral center has to be on the right. And so for glucose, now we just have to remember. So I can just tell you now. The first chiral center, number 2, is to the right. Number 3 is to the left. And number 4 is to the right. So really for glucose, all you need to do is remember one thing. And what's that one thing? Exactly. Just remember that number 3 has what configuration? S. That's all you need to remember. And then you will always draw glucose. Just put everything else on. Just make everything else R. Just make the number. All you need to remember is to make number 3 S. And so this is D-glucose. Excellent. Exactly. Her question is, if you wanted to make L-glucose, and let's just go ahead and draw L-glucose. So for L-glucose, do I need to put if I want to make that the mirror image, do I need to put the O on the aldehyde on that side to make it the mirror image? It doesn't matter. It's not a chiral center. It's flat. So it's the same both ways. It's flat. But these others are not flat. 1, 3, 4, 5, and CH2OH. And so to make L-glucose,
D-glucose is what's in your body then, right?
exactly, D is in your body.
Is L found anywhere? Is it in like different animals?
Some microorganisms have L carbohydrates, and they have them in their cell walls. And when they do that, all of the enzymes for living things basically are D enzymes, so they can cut D carbohydrates. And so if a microorganism has L in it, then if a pathogen tries to come in and destroy its cell wall, it's not going to have those L enzymes, and so it protects itself. We can't digest now. We can't digest cellulose for another reason. Let me explain that really quickly. It's still D-glucose. Now, this projection I'm going to draw now is called a Haworth projection, and so I'm going to just draw this really quickly, and I'll talk about what Haworth projection is later. And so, if that 1 to 4 linkage goes down. See, for glucose, if you have 2 glucoses, this is called an alpha glycosidic bond. Alpha glycosidic, because this is going down. This anomeric carbon is going down, and we'll explain that later. But if you ever have in cellulose, that bond is going up. Did I? Yes, that's right, I did. I did talk about that when I was talking about fiber. And so it's going up. And so that this 1 to 4 linkage here is going up. And so this is beta. This is a beta glycosidic bond. We can't digest this, but we can digest alpha glycosidic bonds. And so this is what cellulose is. That's why we can't digest cellulose. But cellulose is still D-glucose. Good question. So let's go back now. And so here we have D-glucose, and on the right we have, what do we have on the right there? L-glucose. And now when you're looking at the mirror image, all you have to look at are the chiral centers. The others, nothing else matters. Just the chiral centers have to mirror one another. Which one is found in the body? D-glucose. Very good. No time for questions. Went over. Have a great day, you all. Hope you're not late for your next class. I was only late because y'all were asking me questions.